Hello AP Chem students and welcome to topic 7.11, Introduction to Solubility Equilibria. Learning objective for today is 7.11.a, calculate the solubility of a salt based on the value of KSP for the salt. So let's talk about solubility. Here we go. So solubility, so far when discussing whether or not a salt, remember that's another word for an ionic compound, dissolves, we've been using the solubility rules to make a decision. And specifically, we've talked about SNAP, which is that sodium, nitrate, ammonium, and potassium fully dissociate all the time. That's our assumption in AP chemistry. While those can be useful guidelines for salts in general, they are derived from an equilibrium constant that exists for each salt. So let me remind you of what solubility is. So the salt is initially put into water and begins dissolving. Okay, so these are three phases that we're going to talk about here to help us examine the relationship. So then the salt will continue to dissolve. However, dissolved ions will also precipitate. So you're going to see that there is an equilibrium that starts to form. Now, because the salt dissolves faster than its ions precipitate, the net movement is towards dissolution at this point. Okay, at some point, the rate of dissolution will equal the rate of precipitation. And we know from our work with equilibrium in this unit that that means we have reached a state of equilibrium. So the solution will be in equilibrium, but the ions will continue, typo in that caption there, will continue to dissolve and precipitate. So things have not stopped changing. It's just that the rate of change for the dissolution and the rate of change for the precipitation are the same. Okay, so we're going to examine a special point in this process called saturation. So the last picture shows saturation. Actually, this picture shows a point past saturation. When a solution is saturated, it has reached equilibrium between the solid and its dissociated ions. So we call the saturation point that last point at which if you added one more crystal, you would immediately start to see the precipitation. So it's at that last kind of point beyond which you would see precipitation start to happen. So let's look at the dissociation of CaF2 here. So if you add CaF2 solid, so let's say that it looks like that, into a liquid water, then it would dissociate. And you see it look like this. And so remember that when this dissociates, it will dissociate into 1 calcium and 2 fluorides. And so you can see that some of this has moved into solution, but quite a lot of it is still staying in solid form. Because the solid and the water, which is the solvent, are not included in the equilibrium expression, which we call the solubility product constant, KSP, it is written as follows. So your KSP is going to be equal to your concentration of Ca2 plus times your concentration of F minus squared. Again, solids are not included, and we use our coefficients here to become our exponents for our K expression. Because solubility products are always talking about the dissolution of a solid, KSPs will never have a denominator because they will always just have aqueous ions as your products and then a solid as your reactant. So realize that while surface area of a solid affects its rate of dissolving, it also affects its rate of recrystallization. So both the forward and the reverse reactions are affected in the same way by the solid, which means that the equilibrium is not affected by a change in the solid itself, which supports it not being included in the equilibrium since it is a solid. So it still follows our rule. So let's talk about solubility. The substance is considered to be soluble when the KSP for a given salt is greater than 1, which makes sense because that value indicates that the products are favored. And again, in this state, the products are the dissociated ions. So I've got a couple different representations for you here. Both of these are from PhET. This is a PhET called molarity. And so this gives you, this shows you kind of this point of saturation. If you were to decrease the solute amount, you would not see that single crystal. And then once you slide it up a little bit, you do. So this is the saturation point. And then here, this is a different PhET. This is one of the older versions of PhET. This is called salts and solubility. But you can see here that I've got just barely reached that point. And if I add a little bit more, you can see this deposition or, precipitation and dissolution happening there. So you can see I'm showing that with my mouse in the picture. So you do still have some of the particles are coming out of solution and reforming the solid, while other particles are being dissolved from the solid and joining the solution. So it is very important to note that while they are related, there is a difference between the solubility and the solubility product for a salt. So the solubility product is KSP. Solubility has one value for a given temperature, whereas the solubility product is in equilibrium position. However, they can be calculated from each other. I'm going to show you that in just a minute. Okay. So practice 13, calculate the KSP value for bismuth sulfide, Bi2S3, which has a solubility of 1.0 times 10 to the negative 15th moles per liter at 25 degrees Celsius. So if you want to try this on your own, you can go right ahead and pause the video. But I do want to tell you an important fact before you can solve this equation. So when you're finding solubility and you're doing an ice table, solubility is equal to X. Just 1X. That is your solubility. So know that, and then if you want to go ahead and pause the video and try this before I give you the answer, do that now. Okay, so you're going to set up a rice table, and the first thing you need to do is write the dissociation equation. So again, remember that we need to include charges here, and then your subscripts, unless it's a polyatomic, your subscripts become coefficients. So this is 2Bi3 plus 3S2 minus. Initially, we have none of any of your ions, and we get to ignore all the information about the solid because it's not going to be included in the equilibrium anyway. Okay, so then our change is going to be plus 2x for your Bi and plus 3x for your S. This is 2x and 3x. So KSP is this expression, right? Products raised to their powers. And then, of course, we don't have reactants to include because that's a solid. And then remember that solubility is equal to X. So then if I plug in for my concentrations here, you can see we have 2x squared times 3x cubed. And when we do the math for the numbers, we get 4x squared times 9x cubed. So then you need to plug in your value for solubility and for your X. So we're going to multiply 4 times 1.0 times 10 to the negative 15th here, and then we'll square that, and then 9 times 10 to the negative 15th, and we'll cube that. The 4 and the 9, of course, are coming from these terms here. Then when you do that math in your calculator, you get that your KSP is 1.2 times 10 to the negative 71st. Very, 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 very low. We would consider this insoluble. That is an extremely low number. Okay. The KSP value for copper 2 iodate, this is practice 14, is 1.4 times 10 to the negative 7th at 25 degrees Celsius. Calculate its solubility at 25 degrees. Okay, so now we're going to calculate the solubility given the KSP. So basically the practice problem that we did before, except in reverse. So if you want to try this on your own, go ahead and pause the video now. All right, so let's look at the answer here. So again, we're going to start with creating a rice table and writing our dissociation equation. So our copper 2 iodate is going to dissociate into copper 2 plus and then 2 iodate ions, IO3 minus. The formula is not given here. The formula for this would be given on the AP exam. So there's no need to memorize what iodate is. So then we're going to start with 0, 0, and we're going to have plus x and plus 2x, and then we're going to end up with x and 2x. So we're going to write our KSP expression, which is going to be the concentration of copper 2 plus times the concentration of IO3 minus squared, right, because of the 2. And now we're going to plug in our x and our 2x, and so we end up with concentration of x times concentration of 2x squared, x times 4x squared, and so that's for x cubed, and we know that the KSP is 1.4 times 10 to the negative 7th. So we can divide both sides by 4 and cube root, and we get that x is equal to 0.0033 molar, which is equal to your solubility. So again, once you know this kind of fact that solubility is equal to X, then you are good to go on all of these problems when it asks you to find the solubility. Okay, so comparing solubility with KSP values. So I do want to warn you that when you're comparing the solubility of a group of compounds, you need to be careful because your KSPs can only be compared directly when the salts produce the same number of ions. If they do not produce the same number of ions, then you do need to think about it in terms of doing out an ice table and thinking about your value of X. Because KSP values will be given to help you determine if solids will dissolve. You don't need to memorize the solubility rules except for SNAP. You do need to know that those are soluble every time. And then what you'll do is you'll use the KSP values to determine what will precipitate first. So the lower the KSP value, the earlier it will precipitate if you're given a mixture. Okay, and so we'll be looking more at that in the next and final topic in this unit, which is going to be the common ion effect, and that will be the next video that I will be doing very soon. But first, let's talk about what you should be able to do with this. So first of all, you should be able to write the KSP expression for the dissolution of a salt, paying close attention to the charges, and also remembering that subscripts become the subscripts in the formula for a salt, unless it's a polyatomic, become coefficients, right? So the subscripts of the ions become coefficients in the dissolution expression. Calculate the solubility of a salt from the KSP value, and then determine if a salt is considered soluble by examining its KSP value. And that is it. And again, I will see you soon for that common ion effect video.